Freezing is not dropout, right?
No, freezing is not dropout. In freezing, like when you create a network, there are weights and parameters that gets updated during backpropagation. So when you freeze some layer, then during backpropagation, the gradients are not computed with with respect to frozen layers. Okay,
Okay.
gradients are not computed. It doesn't change. It is frozen. And in case of dropout, suppose you have certain neurons, and like suppose there is with certain probability, some of the neurons will be deactivated.
Yeah,
Okay,
from all over the network or from a given layer?
from a given
With
layer.
some,
From
yeah,
a given layer.
okay, okay, fine.
So these are the necessary imports. Then after that, here we are just configuring the device, whether to CUDA or GPU. Okay. These are the hyperparameters like number of epochs. We have set the batch size to 4 and learning rate.
Can you tell me about NN dot functional? Why is it what is it used for?
NN dot functional, basically it has your activation function. Activation functions like ReLU and all that.
Okay,
It
okay.
is so with convolutional neural network, we will do image classification, and we are using CIFAR-10 dataset today. In this dataset, there are 60,000 images, each of size 32 cross 32. These are color images, and they are distributed into 10 classes. These are the 10 target classes. So there are basically 6,000 per images per class. And within these 60,000 images, 50,000 are the training images and 10,000 are the test images. So we will be using CNN for classifying the CIFAR-10 dataset. So this is the hyperparameter. Now here the CIFAR dataset is already present in your Torch Vision. So you will download it in this way into train dataset and test dataset. Now this is transform. The transform, it basically like what transformations you want to apply to your image. O- Like since you're working in PyTorch and everything needs to be a tensor, so this is a mandatory transform. Then you can also perform normalization. Basically, normalization helps in faster convergence. Now you are using like two different transforms, so compose function is used. This transform.compose, it takes a list of all the transformations that you want to apply to the image. If you want to just do transform, single transform like to tensor, then directly you can pass it here. But if you have to like apply several transforms, then this is the way. And i- this is the method, and you transform it, you pass the transform parameter. So you get
So
trained data
transform.
set.
We are transforming the data, so should it be after the after downloading the data set? I think we should include this code.
No, like why? Like it will download, and this data set will have the images that will follow these transforms. Separately,
Okay,
you don't have to do it.
okay.
Okay. Then after that, you have this trained data set. Now we are splitting this trained data set into two, validation and training data set. So like we have taken 20% of the images in the validation for validation and remaining for the training data set. So number of train in this way. So this will give you the length of the train data 50,000. We already know that. Then this indices basically like this will give you the range of values. And after that, we will randomly shuffle. Like this has all, this list will have all the values from 0 to 50,000. Now we are randomly shuffling it and we are creating a split. And once that like this split, it will simply return an integer. Okay, this is 0.2 and this is 50,000, so it will be around 10,000. Okay, so now in this indices 10,000 to later images, all indices are passed to the training index, and from here like 0 to till 1,000 are passed to the valid index. Now this train index and valid index, they are having the index numbers. Now you will pass this to the random sampler. Now this will create the samplers. This will have your data, and then you are creating a data loader out of it. Okay, you are passing the sampler. Now here, like in this, you are seeing that we have
Random samplers here.
random sampler is basically to shuffle this train index. No, random sampler is basically it is creating not it is creating samples, random samples out of these train index and validation index. Basically, your complete data set is then divided into these 40,000, 10,000, and then you're creating samples from it that you are passing to the train loader. This basically just has indexes. This does not have the data set. This has the data set, and that you are
So
passing.
sampler is randomly picking up indices from this 40,000 indices.
Yes, yes. And here, like since we are already we have randomly shuffled it, and it is like it is again shuffling inside this, so we don't need to again shuffle here. Okay.
Yeah, yeah, yeah.
Now these are the target classes. These are 10. Now we are displaying the image. Okay. This is simply like we are converting, since these image, sorry, this train loader, it has image and label. So we are pass these images and label, and we are passing the image. Since it is a tensor, we are again converting it to a NumPy, and then we are using Matplotlib to show it
Yeah,
in
I
this
didn't
way.
understand the operation unnormalize image by 2 plus 0.5.
Because here we have normalized each image na, from
Yeah, yeah.
-1 to 1. So we are again unnormalizing it
But why
using
divided
this,
by 2?
because like see, this is not very difficult. Like this is from -1 to 1. So we are
Right.
transforming it to in this range. Like you can simply compute it. It will come in this way. You can try it.
Okay.
Okay. Then comes the main part. Now we have to create a convolutional network. So we are naming it as ConvNet. Now basically your convolutional neural network, it is composed of like blocks of the first is the feature extraction part, and the second is your classifier part. Okay, so in the feature extraction part is further divided into blocks, where each block is composed of a convolution unit, then an activation function that applies non-linearity over it, and then we do the pooling layers. So in the convolution, basically, in the convolution layer, we are actually applying the convolution function between the image and the filter. So between that, it will perform the convolution operation and it will give us the feature map. On that feature map, we will apply activation function, and then to apply for the non-linearity purpose, like we do in general neural networks. Okay, and then it will be followed by a pooling layer. Basically, in convolution uh, layer, when we are multiplying it with a filter, these filters, like after training, when you look into these filters, they actually look for certain patterns in the image. Like if you go to the inner layers of the convolution network, then you will see that the initial layers, they will be looking for certain patterns, like for a straight line, for a horizontal line. So that way it is working. And as you move on, then it looks for more coarser features, like more uh, features like complete face or texture or color. So that way, and the main functionality, and then pooling layer. This pooling layer, it actually this is actually done to reduce the basically size of your feature map that you get out of convolution layer. And also, like, it also gives you what we say, like translate, like suppose if there is a object at a particular location in an image, okay, then now that image, that object is moved to a, suppose in another image it is at different position. Okay, so the pooling layer, actually because of pooling layer, we are able to identify the same object at different positions also. Okay, it doesn't, so that is the main functionality of it.
So you were
So
saying translation variance, I guess.
translational invariance actually. So convolution, so this is the main feature extraction part of the CNN. Then comes the classifier layers. These are the
I didn't
simple
get, just to stop you. Why do you want need to unnormalize the data before, uh, I mean, training?
unnormalized here.
Yeah, yeah.
No, no, here just for the display to
Oh, okay.
get it into the same scale from 0 to 255 actually.
Okay, okay. I didn't see.
Here
Thank you.
we have, here we have normalized it, and PIL images, they are basically in this range. We have normalized it from -1 to 1. Now, just for the displaying purpose, we have again unnormalized it
Okay,
so
fine.
that it can be displayed. Otherwise, for the training purpose, we will use normalized images only. Normalization helps in faster convergence.
Yes, yes, yeah. Okay.
So now we will start with the convolution block. So basically, we have created a convnet, and sorry, I have named this class as convnet, and it is inherited. It inherits from self this nn dot module. Now we will create the first layer. Now the first layer is conv, wherein input channel is 3. Why input channel is 3? Because they are RGB images, so 3. Now output channel we have set to 6, and kernel size we have set to 5. So in this, we will create input channel, then number of feature maps, then 5, size of the kernel. This is the first convolution layer. Then for the second convolution layer also, the same, but here the input channel will be 6, because now each feature map will have a depth of 6. Then output channel will have 16, kernel size is same. Then we will also get a pooling layer. We are using max pool. Then we come to the classifier part. So we need first classifier layer. Okay. This will have an input. Now for this fully connected layer 1, this will have the output of the convolution, the last convolution layer. Okay, so we have to flatten it, and then we have to pass it to the linear. So first we will compute the dimension. Okay, so what dimension we are getting? I'll set this later. Okay, we will compute. So according to that, I will set it. Okay, now we have 120. Output of this as 120. This will have input of 120 since the previous layer has 120 units, and then 84. This will have 84, and since there are 10 classes, so the output will be of 10. Okay. Now, this is our image. In the forward pass, we'll pass the image. So basically, X will be, first we will apply, the architecture is like convolution, activation, and pooling layer. So we will apply conv1 to the input.
Clear one basic thing. I mean, nn dot linear. What does the first two argument represent for nn dot linear?
In the first, like, what is the architecture? Like you have convolution layer, then you have classifier layer. Okay, so in classifying layer you have fully connected layers. So the input to the first fully connected layer is the output of the convolution block. Okay, so the output of the convolution block is 2D. You flatten it and then pass it to the fully connected layer. So basically, why I have kept this as empty, because during this we will compute. Accordingly, I will fill it and then we will execute. Okay.
Okay.
So like first we have applied the convolution layer. So what will be the dimension of the input after this? Initially, the image size is of 32 cross 32 and 3 channels there are. Okay. And you have a kernel size of 5. So, and by default padding is 0. We are not applying any padding. So it will be what the formula is basically like width for 32 minus the kernel size, which is 5. Okay. And since there is no padding, 0 divided by stride. Stride is 1 in our case, plus 1. So this will be 28. Okay. So after this convolution layer, we will get an image of size 28 cross 28. Now the output dimension, like since there we are applying 6 kernels over it, so it will be 6. Okay. Then after that, we are applying the ReLU. To this output. Then we are applying the pooling, self.pool, to this layer. Now after pooling, again the dimensions will change. So what will be the new dimensions? It will take 28, and here our kernel size is 2. So 2, and stride is 2. This defines the this defines the kernel size, this defines the stride divided by 2. So this will be and plus 1. 26, 13, 14. Okay, so after this, the size will be
Where
feature
did you
channels.
divide, by the way?
Sorry,
I mean, where is the stride argument?
here. The first argument is kernel size, the second argument is the stride.
Okay, okay.
14. Okay, so after this, we have a dimension this. Then again, we will apply the second convolution. The same, this will work. The second convolution. Now in the second convolution, again, the input was of 14 cross 14 input image, and our kernel size was same 15. 9 plus 1, 10. So this will be 10 cross 10. And this, since the output, we are using 16 kernels in this layer. So our feature map will have 16 depth. So this will be 16 cross 16 into 10. In pooling layer, this will have 10. Again, kernel size is 2 and stride is 2. So this will be 5 cross 5. Okay. So, and the number of like depth will not change. So it will be 16 cross 5 cross 5. So after the last convolution layer, the dimension of our feature map is this. So this will be the input dimension. Then we will apply the fully come layers. It will be f dot rel self dot fc1. Okay, this will be as text. Second layer. Third layer. After third layer, no this activation function is needed. And we will return x. So our convolution block is complete.
So, ma'am, in the convolution network, first we have applied max pooling only one time after the second convolution. So, but why we are passing to pooling layer in the
Sorry,
forward pass? In the
in the
forward pass, we are using two pooling layer. So,
because the structure is this convolution block, then activation, then pooling. Then
okay,
second convolution block, ReLU, pooling.
but in the definition, in the init find the constructor, we don't have to pass this twice, like in the pool layer, convolution one, then we have convolution two without any
Here,
pooling. No,
here.
convolution one and convolution two. Okay. Between
This
them,
is this is just the class variables like, and here you are
okay.
using it.
These are the network definitions.
Hmm.
In the init function, we are just defining all the layers. In the forward function, we are using them.
Yes,
Yes.
understood.
Now we are
So do we not need a flattened layer before we feed it into the fully connected network?
Yes, we need that. Sorry, I forgot. Before fully, yes, we need to flatten it. This will have the batch size. Device again. Device. Hmm. Okay, I've not defined the super function. Now we can print this also. So this is the structure of our model. Then these are the optimizer. We are using cross entropy loss. And for the optimizer, we are using stochastic gradient descent. Now this is the usual training loop. What we are doing here is like first we are defining a best loss. This will keep track of the minimum validation loss that we achieve in each epoch. Okay, so initially we are setting it to infinity and then we are declaring train loss and validation loss. These are each list. This will keep the loss, training loss and validation loss of each epoch. Okay, so in this it is similar, like we have to first pass, we are first transferring these images and labels to the device GPU, and then we are uh, passing these images to the model. The model will return the output and this the distribution, and in the criterion we are, that is the loss function, we are passing the output and the label. Now again, like usually in the classifier layer, we have softmax. Okay, softmax basically gives us the probability distribution over the answer space. But in PyTorch, like we are using cross entropy loss, so this automatically computes the softmax of the input, and it then performs the cross entropy. It then computes the cross entropy between the target and the outputs, labels and the output. So we do not need to define a softmax layer out of the in this. It automatically computes it. Because usually like you have classifier layer and then the softmax layer, but that is not needed if you are using cross entropy loss. So this computes the loss and then we perform the backward propagation. It is the usual method, usual like you train any neural network. And then we are computing the final loss in each batch, and then we are appending it. Once an entire epoch is finished, we are adding it into this train loss, and we are getting in this. Then we are setting this for the validation, we are setting the model into the evaluation mode, and same procedure with Nograd, just that this backward pass will not occur in validation. And also, like if we are getting a best loss, like initially it is set to infinite, here I'm getting some error. This. Value on this in this, then set dot pool, and set dot convolution, set dot. Okay, f dot ReLU doesn't assign. Sorry, I forgot this. It is in place. No, this should be 3. Yes. So actually I forgot to change the number here. It was FC1. So here what we are doing is like we are computing the best loss. Like whatever validation loss we are getting, we are assigning, we are comparing it with the best loss. If it is best loss is greater than validation loss, only in that case we are saving the model. Okay. Any doubts?
Best loss should be less than validation loss, right?
Like initially, like best loss is assigned to infinite. Okay, we want the minimum loss in it. So whatever validation loss we are getting, if our best loss is greater than the current validation loss, in that case, the best loss should be that valid loss because it is minimum than the whatever
Okay.
loss we got from the previous epochs.
Okay.
So only in that case we are saving the model.
just one question. I mean, what is the VRAM of a GPU? Just to get
What
a
is
measure
that?
of VRAM. I mean, the VRAM of your GPU. Is it say 4 GB, 6 or
Ha, ha,
2
ha.
GB?
Of my
What is, yes. Just to get a measure of,
mine's 8.
it's 8 GB. I'm not asking about RAM. I'm asking about VRAM. Graphic
Ha,
size. Graphic.
ha,
It is 8 GB.
ha.
Okay.
It's-
One more thing to confirm. I mean, with every epoch, it is computing the loss over 2000 training samples. Is it?
In single epoch, it calculates over the entire training data set, training and validation set. In each batch, it computes over the 2000.
But where did you define batch size?
Batch
Actually,
size up
I probably
here in the
not see this.
hyperparameter. 4. So 4 batch size. We have 40,000, so this is 10,000. Therefore, we have 10,000 like batches.
So part of the
Each,
code is ensuring that we are, I mean, assigning the input in batches.
yes, yes, we are assigning here. This train loader, it creates batches, and each batch is of size 4 in this case.
Okay.
Since we ran it for 5 epochs, so we have 5 training loss and validation loss for each. Then we will plot it and we will evaluate it on the test dataset. Okay. Then we can even look into the freezing. Here, like whatever best model that was saved here in this path, we are using that. We are loading it from the path and using the best that model for our evaluation. In first, we'll print the model. This is our site. This is our model. Okay, now we want to freeze some part of it. So we have a children function. Okay, so this basically children function, it basically returns it. It gives you a way to look into the layers of your model. Okay, it returns an iterator. and these child, it will tell you the layers. Okay, now like using this, we are having access of each layer of our model, so that we can like freeze certain layers and unfreeze certain layers. Now suppose if your model is very complicated, like here we have just single individual blocks. Now suppose like this is one block, this is another block, so we can use again children method on child to obtain further layers, like inner layers of it. But here we don't need it. We'll set a counter to keep track of the layers. Okay. See, we are
So
getting.
we'll iterate the layers and freeze one of
No,
them.
we are. Yes, we are just iterating right now.
Okay.
Okay. Now, like we have got access to the individual layers. Now we want to access their parameters. Okay. So for that we have parameters function. Now we are accessing the parameters of this. Okay. So these are all for the first layer. This is the entire parameters, and it is by default, it is set to true. Okay. Now we can change using require grad attribute. We can set it to false. Okay. This parameter, like if we see the total number of parameters before, now you will see
They are the same. Yep.
Because we have frozen all. No, it should be 0 actually. But this is wires scratch. Now you can see, like, since we are setting every gradient to false, so we are getting 0. Initially, like, there are 62 this many. Now since we are setting every one to 0, so it will be 0. Now suppose I want to just set the first layer parameters, just froze the first layer parameters and not the others.
Just to stop you, I mean, one thing, if I want to know the total number of parameters from layer 1 to layer 2, I mean, weight parameters and bias, how do I actually express this in code?
That I'm telling you.
Yeah.
Okay. So suppose just the first layer I want to set. So what I can do, I can set if count equals to 1, only in that case sorry, count.
I think we should set to 2, I guess. Counter is equal to 2.
If counter is no, for only first one I have to set it. See, you have counter equals to 0, then
Yeah.
counter plus 1. Only the first one I have to set it to 0. So then in this child parameters, if it is equals to 1, okay, yes, I have even updated it here. And in child dot parameters, then we are doing parent equals to this. Actually, indentation is fine. Okay, we got child. Let's just play.
Actually, I think we should remove this one, parameter that requires underscore grad is false. Because the moment
Why?
you do,
No, actually, I want to set only first layer parameters as false. Okay. So, like, I'm having child this in children. Then, if count is equals to this 1, then
you want to freeze the first layer.
yes. Then child of parameters. And after that, can do this. This is setting it to false.
In the print function, the last print function, you have to change something. If p dot require grad, here you have to write.
If it is true, only then it will be counted. Wait. This is It's not coming. Then put in some here, P, and model of parameters. If P
So I once check p dot require grad equal to false, and then check what happened
where
in the last print
Acha.
function. If p dot require grad equal to false, why all the parameters are freezed?
It is not freezing actually. Suppose I have counter equals to 0, counter layer 1. If counter is equals to 1 for the first layer, for the second layer should be simply print, I think. अगर ये ट्रू है तभी हम इसका सम निकालेंगे.
You can do one thing in the iterator itself. Let's say for let's name this FC1. Let's store it in
We can
variable name.
even we can even do name dot parameters. So
Say for name comma child in this model dot children. Let's say if your name is equal to let's say FC1, then for parameter in this child dot parameter, I'll just set this required underscore grad as false.
wait. Oh. Um. अच्छा. This is happening. Okay. See, we have named parameters also.
Let's remove the counter and try with name probably.
Wait, name actually for that we need name parameters. Only in that case we get a name of it. Which this works? Why is it not
we
working
should
now?
we have to search model.name_children. There, I think the name parameter is can use
Their model dot
model.named_children for child in model.named_children.
this
I'm saying
one.
that no. This
Yeah.
will do. Yeah. Just try with this model.named_children.
Then you have name and child.
Yeah.
Okay. And if name is equals to con1.
I think it is FC1, right?
Layer 1 is convolution layer.
So we are freezing the convolution layer on it. Okay.
It is still coming as 0. इसमें कुछ मिस्टेक हुई है क्या कंप्यूटेशन में? When we are not doing any of the counter, without any counter,
Yeah, you can try this without counter. I think you have to set the name also, right? If you're equal to conf.
No, here I'm not setting any like completely entire model I'm freezing.
Okay. Yeah, so if you freeze entire model, then trainable parameters is 0.
But then if I set the counter, why is it not working with the counter? Children. One. I cannot. I'll update this and upload it in the Moodle. Oh, sorry, in Teams. I don't know
Okay.
why this is not working.
Mm,
I will debug this and then upload the correct one in the
okay.
Teams. Okay.
Thing, I mean, the first for child in model dot name underscore children. Just write this.
For child
The
in.
first model dot named underscore children.
Hmm.
Yeah. Then you just
I-
remove this count. And
that and here name.
yeah, if your name is equal to for name comma child.
Um,
So
see,
if
we will
your
also print the name initially just to see what names it has. Okay.
no after print name, let's give the if block.
No, wait. Just I want to see the names. Then I will give. Okay. If
Your name is this con1. And this next for loop should be inside this if block.
yes.
And then we'll set parameter dot. Now probably you can try.
No, even in this case, it is giving trainable parameters equals to 0. But this should also work. Maybe
Print statement we should recheck once.
we have sum. Then we are computing the sum of it. Equal.
Just try using FC1. Let's see what happens. No.
But basically, this is how we freeze the layers. I don't know why this is not working. But once I will debug this and then I will upload the correct file in the Teams. Okay.